right, so it's great pleasure and great privilege to introduce our speaker today, Alexey Belyanin.
Enormous pleasure.
It is. And of course, Alexey is a returning guest at this show, at this 11:30 show on Tuesdays. And Alexey is a professor at Texas A&M, and Alexey has been here at this university for nearly quarter a century, right, since 1999.
Indeed, yes.
According to your CV, real CV.
You studied it hard,
I
obviously.
did, not the one that you sent me though. So I studied the real CV, the real CV.
Sorry.
So an interesting thing and very characteristic thing about Alexey is that every group, every constituency here at this department claims Alexey a part of it. So everybody, each group wants Alexey to be a part of this group, of course.
Except string series, of course. They don't want anything to do.
But still astronomers, you have some massively cited and impactful work in optics and astronomy, and not necessarily optics, by the way. And then high energy physics, so you have work published in that area as well, of course, condensed matter. But we truly believe that Alexey's heart belongs to this group, so it belongs here, and he's a part of this community, part of this group.
That's because we hired you first.
Sure. And also you have the largest concentration of Alexeys, you know.
Right, so we have this great club of Alexeys. Now, Alexey has graduated from Nizhny Novgorod University, right? With honors, of course, Lobachevsky Nizhny Novgorod University. And then he got his PhD from the Institute of Applied Physics in Nizhny Novgorod. And then, of course, he spent some time working in this prestigious institute in Nizhny Novgorod. And then in 1999, he ended up here, and now he's a full professor and associate dean.
No,
Associate department head.
But no financial responsibilities. Don't
Anyway, so associate department.
Just working with undergraduate students.
Associate department head, which is the most important part, and of course, he is such an important part of the outreach, of the overall outreach of this department, and this always amazes me of how it all works. And of course, Tatiana and Alexey are the driving forces. This is one of the aspects that makes this department truly visible among general public, not only professionals who highly respect the A&M group. So yes, the fact that Alexey is of course a true hero from our own ranks should not prevent us from giving him the warmest welcome here at our seminar.
Wow. Thank you so much for this extremely kind and generous introduction. I'm afraid it's only going to be downhill from here, from now, but yeah, let's see. So anyway, well, actually, this is just kind of part of the things. I was going to talk about kind of collection of, I don't know, problems related to dynamics of open quantum systems that are strongly coupled, and they exist in highly dissipative cavities, which is very popular nowadays. And also, we have another whole group of projects related to properties of materials, some fancy materials, nanostructures, topological materials, and people who are working on it. One of them is here, is Dr. Singh Ashutosh, and also there is Maria Sebastian, my graduate student, but this is not what I'm going to talk about, maybe some other time. You know, these topological materials are really fascinating, not only as, you know, the electronic properties, but also optical ones. But this is more kind of hardcore AMO thing. And by the way, speaking of undergraduates, 4 undergraduate students and also another of my postdoc Jitendra participated in this group of projects in different aspects of them. They all have different projects, which also maybe is saying something that is very simple stuff. But on the other hand, I think they are kind of nice research experiences for them. especially when looking for the graduate schools. So it works now. So, I mean, this slide is now obsolete because it just mentioned some of the problems. So some of these problems, they include many body systems, and usually it's kind of heavily numerical, but we did develop some sort of stochastic Schrödinger equation approach to solve them, which surprisingly does allow you to derive analytically or almost analytically some important results for several problems. And it has more or less level of rigor corresponding to Lindblad-Master equation, actually exactly this level. So it assumes that, you know, everything else which is not included directly in your dynamic system is just Markovian noise. That's, of course, a big approximation. Also, all results I will show, they were developed in rotating wave approximation, meaning that optical frequency is higher than everything, and then everything else is kind of, you know, on top of this, you know, rotating waves as usual. Otherwise, analytic results are very far and in between. So that's with all these things. And also we published in the last couple of years several papers on different aspects, different, you know, problems, and still keep working on it. There are two more papers in the working. So yeah, first of all, since I now have more time than usual, some aspects I did cover in PQE conferences in the last 3 years, I think, but now I have a little bit more time, so I can be more, I don't know, pedagogical. Please feel free to interrupt me at any moment. Okay, first of all, it's all about cavity QED and strong coupling system. Even usually it means that there is some ensemble of quantum emitters, or one of them in a cavity, and interacting with not only electromagnetic modes, but also with other boson modes. You can vibrate something, could be some optomechanics or some kind of trap, or it could be simply phonons or vibrational modes in a molecule. So at the end of the day, it's just kind of strong coupling between fermionic and bosonic modes. And even in the weak coupling regime, there are many interesting aspects in cavity QED, of course, such as, you know, you can control spontaneous decay, both enhance and suppress it. There are many single photon emission schemes based on it. But of course, most fun is when you have strong coupling regime, when the Rabi frequency, which determines the strength of the coupling between the cavity mode and the and your dipole in this case, is larger than all the dissipation or dephasing time scales. And by the way, in I think all of my talk, I will assume that the field is quantized. It's very easy, of course, then to go to classical limit, but quantized field has more fun because now you can entangle these different degrees of freedom. You can use, for example, your quantum emitters as a kind of control qubits in your cavity, and you can play with the degrees of freedom related to your photons as a sort of, you know, signal, like consider the polarization of reflected light or study something about the emitted photons, really depending on your application. So that's why it's so much fun. And of course, you necessarily in this strong coupling dynamics will get an entanglement between, you know, cavity mode degrees of freedom and your quantum emitter degrees of freedom. That's for sure. And this kind of pictures, I don't even remember where I took them, like from Wikipedia or something, but that's the idea, right? So now you're coupled to the cavity mode and you experience this characteristic decaying Rabi oscillations. And in the simplest case of James Cummings model, which will be in the next slide, you'll get this, you know, characteristic ladder of coupled polarity, if you want, states, which in some cases is completely integrated and solvable problem. Well, basically in rotating wave approximation. I will return to it, but now numbers. So there are two kinds of, two schools trying to use these strongly coupled systems for applications. At least when I talk about modern optical development, I'm not going back to microwaves, okay? But if you're talking about, you know, optical quantum emitters, of course, the easiest way would be to use dielectric cavities, such as, I don't know, micro rings, micro disks, photonic crystal cavities, some kind of pillars. And those, of course, are very nice because they are less lossy. So they are characteristic losses in, you know, nanoseconds or longer. So it's kind of, you know, micro to nano electron volts. But of course, they have diffraction limited volume, basically wavelengths of light, well, divided by 2n, right, refractive index. And therefore, they are Rabi frequency, which is, of course, scaling inversely to square root of volume for vacuum Rabi frequency. It's on the scale of also micro electron volts. This also means that since typical good emitters have the lifetime of nanoseconds or so, this means that you would need to go to low temperature limit in order to prevent you from, in order to achieve strong coupling regime. But it's not really scaring people. This kind of limit, liquid helium temperatures are, for quantum information, considered to be a must anyway. So, yeah. And by the way, it's still, if you go to very tight cavities, still cavity decay will eventually be a little bit faster than the one for quantum emitters, if you look at experimental numbers. All right, now entirely different approach is a kind of brute force. So, okay, now we are limited with radio frequency. And what can you do about it? It doesn't allow you to strongly couple to single quantum emitter. If you put just one thing there, I mean, it's not enough, one quantum dot or a molecule. And therefore, the only way so far to achieve strong coupling to single quantum emitters is going to plasmonic cavities. Of course, their diffraction limit is overcome. It's not limited by vacuum wavelengths. And you can get volumes of 1 nanometer cube or even smaller. So nowadays, a lot of papers start with picocavity strong coupling, which means that it's probably hundreds of nanometers in some of the direction, of picometers in some of the scales. But anyway, in this case, you do have gigantic radio frequency. Actually, it can be hundreds of MeV. It could be actually approaching the optical frequency. So for some of these experiments, the rotative wave approximation is not a good approximation, and you need to go beyond that. But of course, the price you pay is that the optical frequency mode will significantly penetrate into the body of the metals, and it will lead to very strong dissipation. So your dissipation scale for your plasma polariton now is comparable to your radio frequency. Again, 100 MeV. So it will be like 10, 20 femtoseconds. So in terms of quality factor, we are talking about quality factors of like 10 or 20. So this is barely a cavity. And therefore, its practical applications for quantum information, say, are questionable. All right, you can do like 3 Rabi floppings, but it's probably not enough. However, for quantum sensing, for example, it sounds more reasonable. So jury is still out which approach is better for any realistic applications. Okay. So, but still, as I said, now, of course, temperature is not a problem. Nobody cares about decay of your quantum dots. It is so much longer than decay of your plasma. So you can operate at room temperature. And experiments where strong coupling to single emitter were obtained. I mean, they exist both with quantum dots and with single molecules. Okay, again, you can actually have very tunable nanocavity, like in one of my collaborators' work in Colorado, Marcus Rashke. You can bring a nanotip, and then the apex of the tip is forming kind of a surface. And if you hover it over the metal, substrate, and then if there are some molecules or quantum dots sprinkled on the top, then you can find a situation where you're right above the quantum dot, and then it's embedded in the kind of nanocavity. So, and then you can continue doing that. So it's, of course, practically probably not much of an interest, but for spectroscopic, and kind of fundamental applications, it's fun. Okay, so you can do better. You can actually functionalize some kind of quantum, not quantum, but metallic dots or spheres, so any kind of structures with some radicals, and then molecules will be attached to it, and then it will be sort of more controllable nanocavity. Also, strong coupling was achieved in this case. Anyway, back to math, right? Because we are trying to learn some kind of theory aspects of it. The simplest and completely solvable problem in rotating wave approximation is when we have one two-level system, like quantum dot, qubit, coupled to the single mode cavity field. Then only 2 degrees of freedom here. It is still painful because it's like Rabi model, because you still have counter-rotating terms in the coupling between the, your qubit and your bosonic field. But of course, when you go to rotating wave approximation, which is meaning all scales are smaller than optical frequency or energy separation W, then you get James-Cummings model, which is exactly solvable by any approach you want. Also, some other notations here is that the very important concept is field normalization. So the field is, of course, some, operators, creation, annihilation, but times the spatial profile of the field mode. This spatial profile of the field mode should be calculated by using classical electrodynamics, always with proper boundary conditions in a cavity, which can be very complicated. I showed you some examples of very involved cavities. Of course, nowadays, you can just throw it into console or something. Or if cavity has high symmetry, you still calculate it analytically. So that thing is classical. And what makes the overall field quantum, what makes my Hamiltonian look like this? By the way, I dropped 1/2 because it's not important for any of the stuff that I'm going to talk about. It's canceled out. But in principle, there is 1/2 here if you want. It's really not important in rotating wave approximation. So the normalization of this field is again classical, but if you equate the field energy with h omega, h bar omega, then you will get the standard Hamiltonian like this, which will coincide, of course, with classical Hamiltonian, e squared plus b squared. Well, with some derivatives coming from the fact that your medium is strongly dispersive. So already from this normalization, you see that this amplitude does scale as square root of omega over volume. So you do need tighter cavity.
In this field, well, will there be any model expansion at some point? Because
Into modes. Yeah, I mean, here I assume that there is only one mode, but of course, in principle, for any structure, you have many modes.
Because this E of R should belong to each mode.
Of course, if you see it's one mode, but if you have many, it will be sum over all of them. It does not create any principal difficulty, but yeah, it's of
Then
course.
there will be many couples.
There will be many couples. You will have more degrees of freedom. That is true. Yeah, sure. Again, it's not a principal difficulty, but it's algebraic difficulty. Yeah. Interesting that for nanocavities, usually it's not a terrible problem because since modes are very far and in between in frequency domain, for your quantum emitters, usually only one or very few modes are really coupled to it, resonant to it.
This is important.
Yeah, this is important. But when you have large cavity, of course, with very dense forest of modes, you would need to include all of them for sure. That's true. Yeah, it's a very good point. So anyway, yeah, how do you solve this equation with this Hamiltonian? So far, no losses, notice, right? No dissipation, no noise. You have this ansatz in terms of suitable basis. This will be my, if it's two-level system, fermion is only like 0 and 1, and your boson is just ladder of n, right? So from 0 to infinity. And then in Schrodinger's picture, when you substitute this into Schrodinger's equation, then your equations are split into pairs, and they are uncoupled from each other. And your ground state equation, C00, is completely uncoupled. It has its own free evolution. So, of course, you're just dealing with a set of two equations. You can easily, and they're linear. You can integrate it. Well, of course, in Schrodinger's picture, every problem is linear, but you just have more equations as you go to more and more, to larger and larger bases, right? So you can solve it immediately. You will get like, you know, these eigen energies which show clear anti-crossing like this at resonance, right? Between the cavity mode and your qubit. You will get this for the occupation probability, C. You will get this typical Rabi frequency behavior, which shrinks in amplitude when you increase the detuning. Everything depends on this Rabi frequency scaling. So you get a complete solution in this case. You can also get complete solution in any other formalism. But note that, for example, if you are interested in this nonlinear dynamics, meaning that populations are affected significantly, so they are flopping really, then Heisenberg approach encounters difficulties from the very beginning, because you have nonlinear operator valued equations. And in some cases, now it's becoming more like a matter of art. For Jaynes-Cummings problems, there are actually exact operator valued integrals of motion. And you can construct your solution based on this operator valued equations. Of course, it leads to the same result. It's integrable problem no matter how you approach it. But imagine that you have more degrees of freedom. Then Heisenberg approach is usually used when you have perturbative regimes, when this, you know, like field is weak enough and you can apply some perturbation theory. Of course, master equation, dense-symmetric equations, they always work. When you increase number of degrees of freedom, they usually become heavily numerical. But the benefit you are getting is that, of course, you can include dissipation and noise in all kinds of approximations, not only Markovian. I mean, getting harder and harder to treat it even numerically. But yeah, now Schrodinger's equation, as you saw, one huge advantage of Schrodinger's picture is that your equations become linear, no matter how degrees of freedom you add. But again, your Hilbert space grows, your basis grows, and then you are eventually hitting the same kind of numerical issues. And moreover, in this two approaches, it's completely clear how to make it, how to add dissipation and noise, coupling to the reservoirs. How to do it in Schrodinger's picture. Of course, you can always add some gamma decays. It will be Weisskopf-Wigner picture. Then you will get exponential decays of excited states, but your norm won't be conserved. So you do need to add some noise. It will compensate for, non-conservation of the norm. And then there are a lot of methods like this. Quantum jumps, unraveling, which is essentially also quantum jumps. They're usually heavily numerical, and they involve some kind of Monte Carlo, for example, procedure in order to have these jump sources explicitly. I will show you an example. But again, how am I doing? Already too many details, drowning in details. I thought it will be nice to have your overview of different methods, how you include open quantum systems. They are all open in the end, and therefore it's actually important. So remember, there is this whole Langevin philosophy, if you want. So when you include coupling to reservoirs in such a way that you had Heisenberg equation of motion, purely unitary evolution. Now you're adding relaxation of your system, but then you have to add noise in such a way that they match each other in the following way. First of all observables are calculated not only averaging over initial state, psi naught of your system in Heisenberg picture, but also over statistics of this noise. And furthermore, both the commutators and correlators of these noise terms are uniquely determined. This one basically can be found from conservation of the commutation relations for your original operators. And most importantly, when you calculate this stuff, you will encounter the correlators of your noise term. Now, those are a little bit more subtle, but usually you will fix them by requiring that your system approaches a physically meaningful equilibrium state at t equal to infinity after all interactions within system kind of disappear. And then, for example, they could approach thermal equilibrium or some kind of incoherently pumped equilibrium if it's a laser-like problem. So this is the approach. And for example, if you have just a mode sitting in a dissipative cavity, the equation of motion for this mode C will be like this, right? So you add dissipation, you add some yet unknown noise. And you can do the same for the dagger, right? For the creation operator. And then you immediately will see that if you define commutators like this, so it's proportional to mu, to dissipation, it will ensure proper commutation relation for the C field. And if you determine the correlator like this, it will ensure that your photon number approaches the Planck distribution at equilibrium. So you can always do that, right, in Heisenberg picture. Now the question is, can you do the same in Schrodinger's picture? In principle, you can take any of your Heisenberg's equation for any arbitrary operator J and G, and you can apply, inverse unitary evolution. Basically, you can shift time dependence from operators to the state vector, right? You can do that. And then you will obtain, so like now you are determining your observables again after noise averaging, but with psi of t. And this G will be in Schrodinger's picture, not time dependent. And that's very nice. You will get something like this, but now your noise term as a result of applying this directly, it will depend on your specific G. So it's not a general approach. It's not good in this case. So you want an equation which should look like this. Just similar to this guy, you see? So dissipation, unitary evolution plus noise. But you want it to be completely universal so that you write it down. It's not an art to figure it out. You just write it down as in a general form, okay? And it turns out that you can do that. You can define uniquely this R of T, this noise vector, and also the non-Hermitian part of your Hamiltonian, which describes the dissipation. Basically, there are two ways of doing it. One of them is based on, you can derive it from Heisenberg-Langevin method still. What I will show you is deriving it from density matrix. So postulating the density matrix is a gold standard master equation. Basically, what you do is that you will still assume that whatever solution you consider, you substitute some expansion into basis into your Schrodinger's equation. You will assume that all your occupation probabilities, they approach thermal equilibrium in the absence of any external perturbation at very large, at very long time moments. And I also want that the equation of motion for these dyadics, it is averaged over the noise. They will be equivalent to the equation of motion for my density matrix elements, okay? And obviously, this is just a mathematical thing, psi of t obtained from this equation. It's linear equation, you can integrate it out. It does not have any direct physical meaning by far, right? It has a random noise term after all. And therefore, it's only used to calculate observables. And of course, only after you average over statistics of your noise. And this is easy, obviously. First of all, the norm is conserved. That's one of the requirements to R. And second, this is second requirement. And third, when you calculate any observable based on this psi, again, you will encounter some correlator of this noise term, and then you need to specify it. Let me maybe show you how you can directly derive it from the Lindblad master equation. You have density matrix, which is unitary evolution plus your Liouvillean. In the case of, Markovian noise, this Liouvillean has a very simple form. It's local in rho, right? So it's just some kind of bunch of operators, and each of them, and some relaxation constants here, gamma, right? And each of them is well defined for particular model of your reservoir. Harmonic oscillators, like some bosonic reservoir, fermionic reservoirs, it's all well known, it's in the textbook, including yours. So everything is Emin and Zuhails. Everything can be found for simple reservoir models. Now, it's also known that in this case, and that's basically nature of unraveling of master equation, right? When you prepare it for some of the quantum jumps approaches, you can split your L into two parts. One of them can be written as commutator with Hamiltonian, with density matrix, I'm sorry. So I can add it as anti-Hermitian part of the Hamiltonian. And what is left is that in particular for this Lindblad form. And in the method of quantum jumps, it's used as a generator of jumps. But now I won't. I will use it instead to define my noise vector in the stochastic Schrödinger equation, or our version of it anyway, okay? So now I want to go from here to there. And my prescription is like this. I will use this H effective, this non-Hermitian Hamiltonian to describe evolution, including dissipation. And I will compensate for all problems that I included by this, like non-conservation of norm, etc. Basically, violation of fluctuation dissipation theorem with appropriately constructed noise vector. And my statement is this noise vector is uniquely defined in the following way. So imagine that I'm solving my psi in certain basis alpha, right? So I'm getting some differential equations for C and some components of this noise vector here. Now my statement is, as long as I postulate this for dyadics, and as long as I postulate that my correlator of noise vector is directly proportional to the matrix element of this leftover in Lindblad formalism. So the stuff that generates quantum jumps for the master equation is also the one which uniquely determines the correlator of R in my stochastic Schrödinger equation approach. Of course, R also have zero average as itself. So its correlator is that. Yes, there was some question. Go ahead on some stochastic methods. This of course well known. What I described does not differ from any Langevin approach. Sure. What people do in, for example, unraveling of Lindblad equation is that, okay, this is Lindblad master equation. And now they do the same thing with the Hamiltonian. They split it into the non-Hermitian part here and whatever is left, because the same thing is left here. And then they use this, this whatever is left, you see the same actual structure as the source of jumps, and they solve this equation in this form as, like evolution affected by dissipation in between, and then some sudden jumps at whatever arbitrary moments of time. Obviously, this method is very, very conducive to be solved in some kind of Monte Carlo approach. It just kind of begs to be solved in this way. So a numerical approach, it's very heavily used for sure. But again, I'm not solving for rho now. I am solving for psi, or rather for its components in any suitable basis. And what I'm trying to say is that I'm getting smallest possible amount of linear differential equations for this psi, which in many cases can be solved analytically explicitly, just linear algebra, okay?
What do I do
Yes,
to put into a probability amplitude equation
Yes.
of motion the decay from one to another? If I'm decaying outside
yes.
this Hilbert spatial problem.
No, one to another is perfect. You will show some examples.
Okay.
Okay, like this, I will start from system with only 3 degrees of freedom. So you will show explicitly, but there is nothing else. But in this approach, you are adding some exponential decay here, but it has to be balanced, if you want, by corresponding noise term R. So as you see, this correlator is proportional to this thing, and this thing will involve some of this relocation constant. You will see. And I was not even going to describe make any revolution in, frankly, quantum mechanics. There is nothing revolutionary in Langevin approach or in its application to Schrodinger's approach. And of course, you can always poke holes in it, and you will say that eventually, if you include everything as you should, exactly, arbitrary reservoir, your arbitrary reservoir will mix up all degrees of freedom. You still will need to sample this whole exponentially large Hilbert space. And you are doomed no matter you do. You will end up with the same amount of equations as for density matter. That is true. However, again, making approximations which may or may not work depending on your problem. For example, room temperature reservoir for optical transition is still 0 temperature reservoir, things like that. You can't get by solving on the limited number of equations. Or, for example, if you assume that you interact only with one photon, so very few photons in your mode, again, not sampling too much of your Hilbert space. And from those maximum energy, you can only go down and not up by interacting with noise. Again, you have a limited set of equations. For example, let's consider the simplest case, which is of great practical importance, however, when you have your cavity QED, but interacting your quantum emitters like molecules or atoms or quantum dots are interacting not only with photons, but also with some vibrational degrees of freedom, like vibrational transitions in molecules everywhere here, or quantum dot embedded in solid matrix interacting with some phonons, or cavity optomechanics. I mean, this is for a lot of molecular applications. So this interaction is not reservoir. So you do interact with some small amount of vibrational modes which are in resonance, or they're significantly affecting you. Cavity optomechanics is another huge field. The original paper equating Raman and cavity optomechanics is probably wrong, but anyway, the idea is still there. So now you have kind of mechanical vibrations, like say your cavity is modified by some vibration acoustic modes or some kind of cantilever. In this case, actually, Josephson junction, which has some, vibrating cavity here. So there are a lot of things like that, which also involve coupling between, again, fermionic degree of freedom, your optical transition, your photons in a cavity, and your phonons, any vibration. Now, as I said, in quantum dots, it's a standard observation that people observe when they observe decay in some interband transition, some exciton in the quantum dot. Then they routinely observe phonon replicas, which means that it was not correct to treat phonons in your crystal matrix as a reservoir, as a Markovian reservoir. Some of these modes do participate, I mean, they kind of parametrically affect your optical transition here, and they create satellites. So there are many approaches trying to include these non-Markovian effects as some sort of perturbation. What we can do here, however, is that since we don't pay such a huge price on adding more and more degrees of freedom, we can add those few, let's say one or more, or like 2 or 3 phonon modes, creating those replicas as exact dynamic degrees of freedom and treat them non-perturbatively. And everything else will still be Markovian noise. So like simplest situation, which is already leading to non-trivial coupling. So it's strong coupling, but at nonlinear or parametric resonance. Imagine a molecule, just for example, which has a combinational transition, which changes not only electronic, but also vibrational quantum number. This is very loud transition still for most molecules. And then it will decay parametrically, if you want, but with resonance to a photon and a phonon, or any combination here, a phonon and a photon doesn't matter. I mean, they all have to be at the top, of course, included. So instead of two-wave resonance, say electron transition is equal to photon frequency, or vibrational transition equal to phonon frequency of some mode, you are getting this combinational, parametric resonance, which can be also strongly coupled. Now you will say this is an exotic situation. Actually, this is kind of common situation in many experiments. First, experiments too, but first let me show you what kind of Hamiltonian you can obtain if you just literally add some, add some acoustic or vibrational mode. Let's say you have the standard coupling between your two-level qubit and a photon mode, but then imagine that something is shifting your qubit with quantized amplitude. So I want to quantize this vibrational mode too. And then what will happen here? Well, it's getting very ugly. But assuming that this Q is very, very small and it's proportional to some, creation annihilation operators of my phonon mode, eventually you end up with parametric Hamiltonian, like this. So, like you create an electron excitation, and then it decays into a photon and a phonon, or vice versa, right? And you can do it for any possible combinations. And then if you expanded this E in Taylor series to Q, then you will get something like this. Your effective nonlinear radio frequency here will be not your usual radio frequency. It will be proportional to the gradient of the field. Okay, that sounds like super ugly and very artificial situation. It would require very small cavity in order to be sensitive to the shifts of, say, your molecule, your ion in the molecule will be shifting with respect to field distribution. But it turns out that, well, actually every model Hamiltonian that people use for including phonons or vibrations, it can be cast in the language of this parametric decay. Let's consider a molecular Hamiltonian, which is basis of, starting point of many books. I have photons, I have electrons, I have phonons or vibrational modes there. Let's say only one, just one transition I care about. Now I have standard two-way electron-photon coupling, just your normal Rabi coupling. But in addition to that, I have a situation when phonons modulate the energy of my electron transition. This is what creating these replicas that I showed you in experiments, right? This is called Huang-Gris theory. And the corresponding factor is called Huang-Gris factor. Again, it's a standard Hamiltonian in molecular dynamics to include vibrational modes into the picture. Now, there are not even photons here anywhere. So where is photons? Of course, this is usually written in this way when there is no cavity, just a molecule. But let me, I will make a point in the next slide, why this Hamiltonian is even relevant. And now another approach is, or other bunch of problems, is cavity optomechanics. So now you have a cavity, and something is modulating some cavity parameter. For example, size of the cavity, some cantilever, or some kind of particles in a trap, ions in a trap oscillating. And this modulates frequency, for example, in this case of the laser of the cavity mode. Again, modulation is very small. I can characterize it by some change of parameter G of the cavity. And if I do that, what will happen is that vibrations, this B, modulate now the photon energy, C dagger C, okay, this guy, with the coefficient which is proportional to, again, this kind of rate of change of frequency of mode with respect to my coupling parameter. Okay, so far zoology. How does this Liouvillean look like, and how does it contribute to my eventually stochastic equation for the state vector? That's my Liouvillean, right, as we already discussed. In this case, I have electron transition. Okay, let's consider like a two-level qubit, only this one. I can add more if needed. I have photons and phonons. So as you see here, these terms in L include explicitly relaxation constant, these gammas or mu's for the photons and phonons, and occupation, assuming here thermal, of the states in my reservoirs, right? Obviously, this is weak coupling to reservoirs in this case, but that's a structure. And now you will say, what an ugly structure. Again, it's a little bit involved, but still you can easily calculate all the elements that I introduced here. So I assume that I know all the temperatures of all reservoirs, electrons, photons, and then basically I end up with having equations of motion. So now you have 3 degrees of freedom: phonons, photons, and fermions, right? Now there are these coefficients with 3 indices. And now it turns out that again, here, this in rotating wave approximation, these coefficients are separable in blocks of two, where the ground state equation actually can be solved immediately by, considering the norm, conservation of norm. If all fields are quantized, as they assume here, then it's easy to evaluate eigen energy. They are proportional to, of course, both photon and photon quantum numbers. And also, the non-trivial part is calculating these noise terms, of course, always. Now, these gammas are now suitable appropriate combination of original partial relaxation constants of my reservoirs, right? So the detuning is now from the parametric resonance here. And now let me see. So these are my relaxation constants. They are ugly, but okay, this is just linear thing, linear combination of all partial relaxation constants. Moreover, when you observe some spectra, like emission spectra of this system, you can, of course, immediately relate the widths and relative heights of the spectra with all these parameters of the reservoir, so you actually get diagnostics of them. So it's kind of nice. For example, you consider the decay of the excited electron state, but with all other things in the ground state, right? Into ground state eventually. What will you observe? And then you will immediately see that depending on the, rate of relaxation constants of your photons and phonons, you will get, well, anyway, 3 peaks, but with different heights and widths that are completely controlled by those relaxation parameters of the reservoir. You can, for example, emit a phonon first and then a photon, or vice versa, and you will spend different times in different intermediate states, depending on which of the degrees of freedom decays faster. But again, there is one, this is actually an analytic formula for this spectrum. There is essentially what it's obtained by direct integration with those R coefficients. So it's, okay, ugly, but it's still an analytic formula, and you can completely interpret what you observe in terms of your relaxation constant. I will show you just some numerical result. What happens when they are all mixed? When adding capital omega, subtracting capital omega is still small addition. So all these resonances are completely mixed. Then it becoming numerical. Okay, so I mean, fine, sure. Of course, the truth is eventually you don't get any benefit. It's not revolution in quantum mechanics. Eventually, in general case, you get exactly same labor. What else can I say? What you can have in the case of phonons when they are low frequency is that very often it's not even a quantized field. If it's not quantized, then it's like external modulation added to the two-wave resonance between optical transition and your photons, right? Then it seems to be degree of freedom even quantized. So now my state psi, it had 3 degrees of freedom. It was like GHZ state, right? Now it's simply, the bipartite state. And then it greatly simplified everything. Then it's just, you have this vibrational modulation, which creates replicas in your spectra, in your photon emission spectra. So then it's a more boring problem. And as I said, you can, of course, in this case, well, that's exactly this kind of modulation. In this case, it's very easy to do what you said, of course. If phonons are not quantized degree of freedom, then whatever they are just an external force here added. And then you can expand in Fourier series with respect to this omega. And then, the solution is still very, very simple. This is an example when resonances separated at like 2-wave and 3-wave resonances. Now, these things are just numerical. They are Fourier spectra of my occupation probabilities. But just to show, so any cut of them would be like emission spectra. But let me show you what numerics says when they're all mixed. You will have a huge mess. That's why I don't even like showing it. So if omega capital is very small, phonons, then of course you cannot separate 2-wave and 3-wave resonances. And then you're getting something like this, where again, size of each bulb is like the value of the C, absolute value squared occupation, is corresponding Fourier harmonic at a given frequency. So instead of nice, Rabi splitting at 2-wave and 3-wave resonance, they're all mixed together. Your spectrum will be horrible, but okay, you can always do that in this case. Okay, I am running out of time almost terribly, but the good news is that I'm now coming to the example which I discussed recently in January. Of course, I don't assume that everyone remembers what I've been, blubbering about. But still, now what if we have many, many degrees of freedom? But now for a change, I want all of them to be the two-level systems, and I want them to be coupled to a common cavity mode. I should say that it's kind of conceptually equal approach if you have only one two-level system, but coupled to many cavity modes. Equations are almost the same, but well, still. So now this particular problem of n qubits coupled to common cavity mode, it's Tavis-Cummings problem, of course. If qubits are completely identical and indistinguishable, and if they experience exactly the same coupling strength to the cavity field, so Rabi frequencies are the same, then this problem can benefit greatly from the permutation symmetry. And it's been shown now and again that you can analytically solve it without dissipation and noise. And then your Lindblad equation approach also is kind of, manageable. But of course, in many cases, especially in nanocavities, do I have a picture of nanocavity? Somewhere, eventually. Of course, different quantum dots experience very different field strengths. So their coupling strengths are certainly not equal to each other. The field varies on nanoscale. And of course, many quantum emitters, especially quantum dots, or even continuous excitations like exciton in quantum wells, they have very different energies in homogeneous browning, which needs to be taken into account. Any of these things, of course, breaks permutation symmetry and makes your life either slightly more miserable or very much more miserable, especially if they all have different transition frequencies. Then it's like chaos. It's a bunch of coupled nonlinear oscillators with different frequencies. It's multi-periodic motion, terrible. Now there have been great advances in analyzing this again recently by Franco Nori, who has been here, right? I think recently, and he was at PQE. And for example, this recent paper directly builds on James Cummings' problem using this quantum jumps approach, of course, that he's kind of very well known for. And he uses the permutation symmetry, making this approach quite manageable. But remember, I want a situation when it's not the case. There are abundant experiments in nanocavities where the coupling strengths are very different, and also transition frequency. Quantum dots in some kind of bow-tie nanocavity, quantum dots attached to a metallic dot, a metallic sphere. All kinds of nano antennas have been tried, and all kinds of impurities, so quantum emitters have been attached to them, achieving strong coupling regimes. So tons and tons of literature. In all of them, in homogeneity of the field is very important. So we have different energies of n qubits, and we have different coupling Rabi frequency strengths of n qubits. Probably I should move faster, and I'm sure I don't have time for my third example. But anyway, let me consider situation which is analytically tractable. When I consider only single photon excitation. So all my dots were in the ground state, and then a single photon comes and gets absorbed. And my coupling to reservoir does not promote them to upper states, just thermally. That's what one of the things we discussed right now with Girish, right? So I'm not trying to sample vast state of all this n qubits. I'm still limited to single photon excitation. In this case, a lot of things can be, again, you're solving some linear system of equations. I'm pretty sure I have some of these D's. Now, that's what I meant. You see, they do depend on my C's, which would be like diagonal density matrix element. This is a problem normally. So because I determine my correlators through things that I don't yet know, right? So this is a problem, of course, which in generally is making my life as miserable as solving density matrix. Again, as I said, you only get around it in certain approximations. But now look, so we have these equations. I know the correlators of all the noise terms. They're still ugly because if they have arbitrary detunings, as I said, multi-periodic motion. All the relaxation constants are expressed through the relaxation of my qubits and the cavity modes. I can easily classify all possible states into bright state and dark states. There are many, many dark states in this situation. They are highly entangled, all of them. So this single photon can be absorbed by these dots in a huge amount of entangled states. Most of them are dark, and this is great. because remember what was my original premise. And by the way, achieving strong coupling is also easy because my collective radio frequency is always very, very large. Yeah, that's why people play with molecular ensembles and dots. So let's say I have amount of excited qubits J is very small, let's say 1, or anyway, much smaller than N. Then statement which comes from this analytic solution or semi-analytic for different transition frequencies is that even though each of these qubits is strongly coupled to the same cavity mode, the resulting excited state is arbitrary, not bright or dark, but its bright part of it is robustly very small. So I excite this single photon is absorbed by my system. Small bright part of it is decayed very, very fast, tens of femtosecond, because it's nanocavity. What is left as a result is that most of the population remain almost one. So one tiny part gets decayed. So my system remains excited for as long as my individual qubits live. And this is very nice. It's like dissipation drives your system into the dark state, one of those dark states. And this is very robust process. So this will stay there not forever, but again, remember, this is femtosecond, and my qubits live from nanosecond to picosecond, depending on the temperature. By the way, the nice thing about this solution is this it's entirely analytic when the transition frequencies are the same. One of the undergraduate students developed a nice solution to this quasi-electrostatic problem, a nanosphere about a metallic plane. It's a serious solution, like in terms of infinite series of image charges for the ideal metal, of course. And then you can write very nice analytic approximation. It's a rapidly converging series, turns out to be. So you can use it here. You can sprinkle here a random distribution of my dots, randomly distributed within some circle below, which is a standard experimental situation usually. And then you can generate these actual analytic curves, but you can generate how the bright state dies if you excite it in bright state. But now most of the population stays in one of the entangled dark states. So the emission spectra of intensity, as you add more and more of these qubits and still single photon excitation, not only they get separated by collective radio frequency, but of course the amplitude also gets greatly reduced. So the probability of emission is now suppressed by 1 over n, which is kind of nice because when n is already more than 10, it's a significant factor. Now, as I said, when you have more than, I should really shut up already. When you have different transition frequencies, there is no exact analytic solution to those linear equations because they have time-dependent coefficients. You cannot get rid of it. Now you have multi-periodic dynamics of individual qubits, which is not integrable. You can integrate, of course, numerically, and then you get the same result. As long as my collective radio frequency is larger than the spread of this eigenfrequency, I think this is a sign for me to stop. Then, even in this case of dominated inhomogeneous broadening, huge spread of individual frequencies of quantum dots, you still get a situation when the population, sum of all qubits population stays, and only teeny tiny part, like 10 to the minus 4, it kind of leaks out of the cavity, leading to slow decay. Of course, when you decrease collective radio frequency, it becomes smaller than spread of the original transition frequency. Everything dies out very rapidly. So then you lose property. Fortunately, when number is large, this thing is large. They are all different, but again, they are roughly scale as square root of n number of qubits. So you still have this, robust formation of the dark state. And as again I discussed, when you increase number of photons that are absorbed, so energy of excitation, everything quickly deteriorates. And eventually, if you have multi-photon excitation, you can only check numerically. Okay, you can still have this formation of dark states, losing some of the excitation. But this is already purely numerical things. So eventually, all the benefits are lost. Okay, I will probably stop here. Many other examples we solved, including only 2 qubits. And the dipole-dipole interaction, which creates this kind of symmetric, antisymmetric, entangled dark states. Also cool. time-dependent modulation, like your tip is moving or your plasma mode frequency changing by some voltage. So all these model problems can be, well, relatively easily solved. So it's a huge sort of playground. And even propagation problems, like you have a photon, it gets critically coupled to the cavity with some K2, which gets decayed into signal-enabler photon. You can, play with parameters of the coupling in such a way that the photon primary mode of decay will be this spontaneous decay. So you can get kind of a source of, entangled photons out of here. Of course, it also requires low enough losses. If absorption is too high, then you're dead. Anyway, thank you so much. Sorry for staying over time, but I had to field a lot of questions. So it's not entirely my fault. It's your fault too.